Okay, we're going to be focusing on free body diagrams. Starting off, we're going to explain non-contact, later on explaining contact forces. The first one is going to be the law of gravity. In other words, it's what keeps us on the earth and allows us to, live and not fly off. Then going into weight, which is just your mass times gravity, which is negative 9.81 meters per second squared, and that's your gravitational force, gravity.
So these are the contact forces, which is created by the reaction between two different objects with each other. This is provided to us because of Newton's third law, which is the law of action-reaction, stating that for every force exerted by an object, there is an equal and opposite force exerted on that same object. So this equation right here is Newton's third law of action-reaction. So you can see the sum of all the forces within a system or an object, object A on B, is equal in magnitude to the forces of B on A, but it's going to have an opposite direction, which is why we have this negative symbol here. But ground reaction forces, again, like I mentioned, it's what enables us to stay standing on the earth, because the earth is providing a force onto our force of the mass times acceleration, so our weight onto the ground, and that's what keeps us from just falling through the ground into the earth, more or less. So in this case, if we have the ground here and we have a person standing where their feet are in contact with the ground, that's where we have our person exerting force into the ground. The ground reaction force would be at these points of contact of the feet pointing upward, because they're opposite in direction, and the magnitude would be equal to our body weight onto the ground. And then friction is a really important one, because it allows us to not slip out and kind of translate movement so that we can move across different surfaces such as the ground. It acts in parallel to the interface of the two surfaces in contact. So I'm going to draw kind of an example here. Say we have the ground and then someone is walking this direction. They're moving to the right. Each time, you can see here my foot as well. As I move forward, the friction is between my foot and the ground, and as my foot is moving forward, the friction is going to be directed backward across the impending motion of my foot of the same magnitude. So here, if we're moving forward on first contact, the friction would be here, and as our center of mass shifts over our foot, the direction of it shifts of the friction turns in direction, so we can use it as a propulsive force.
So we're going to talk about static friction and kinetic. Static is before we begin to move, or impending motion, while kinetic is actually during motion. Y-axis being your friction force and your x-axis your implied force. As you begin to get closer to movement, you actually increase to your instant of motion. Once you hit that peak, you go into dynamic where there's actual movement. The thing is about dynamic is that it's always going to be less than your static friction peak, and then will stay pretty consistent as you begin to move.
So now we're going to be drawing our free body diagram, which is a visual representation of the external forces acting on a system. The double stance phase of someone walking, and so that is when they have both feet on the ground. And since there's 2 points of contact, there would be 2 vertical ground reaction forces acting right here. And then we're just going to label one 1 and the other one 2. And then those together equal the person's body weight. And so that arrow should be about twice as long. And it's over the center of the body, so obviously it'd be over here, but I just want to make sure you see it. And then because this back leg is in the propulsive phase, this force right here, this frictional force, is acting that way against it. And then since the front foot is in the braking phase, this friction is acting opposing that. And so there's that one. We're now going to look at the equations of motion for the free body diagram. And this is how we chose to define our system, and it's a little easier to work out the equations that way. So for the interior, posterior directions, we're going to look at our air vector, and since it's moving this way, the runner is moving in this direction. Since the force of air is moving this way, we're going to consider it negative. And so under this, we're going to put air. And then our frictional force is moving in the opposite direction. And so we're going to make it positive. And write that there. And then those together equal ma of y, the y axis. And then for the vertical components, we have our force of body weight being negative. So we're going to go negative force of body weight. And then our vertical ground reaction force is going in the opposite direction. So we're just going to add that. Ground reaction force. And then that is equal to ma of z.